Simon is a professor here in global health and just came from Oxford a few months ago. He's also the director of geospatial science at IHME. His career over the last many years has focused on spatial and temporal aspects of infectious disease epidemiology to support a more rational implementation of disease control and interventional strategies, so very much in line with some of the implementation science work that we do. His best-known work initially focused on accurately defining populations at risk of malaria, and then also was a co-founder of the Malaria Atlas Project. He then worked on a similar European Union-funded initiative around dengue, and then has now come to IHME to work with Bill and Melinda Gates Foundation funding and IHME support on rolling that out to other infectious diseases, which we're going to hear a little bit about. He obtained his doctorates from the University of Oxford, which I was pleased to note he remains a member of the congregation. I didn't realize you were a part of a congregation at Oxford, but that's great. And also holds positions at St. John's College and Wellcome Trust Center for Human Genetics. He's published a lot, over 250 peer-reviewed contributions, and has been awarded many, many medals, including the Scientific Medal of the Zoological Society of London, and most recently, the Chalmers Memorial Medal of the Royal Society of Tropical Medicine and Hygiene. And I could go on and on listing them, but I won't, because I want to actually hear Simon talk, not me. But with that, I will ask Simon to come up and talk to us a little bit today. So thank you all for coming.
Thank you. It's an absolute pleasure to be here. And just maybe to temper some of your expectations after that lovely introduction, I am, as you know, Professor of Global Health here in your department and Director of Geospatial Science at IHME now. So I'm Director of currently one person, which is myself. So just we are in a recruitment phase. So again, just to sort of temper expectations there, I just want to let you know the largesse of my current empire. But we'll talk about that in a moment and how we're kind of recruiting and expanding and why it makes sense for me to join in with the IHME stable. So I've been told to prepare a talk for 30 to 45 minutes, which I've done. So there's about 30 minutes on malaria and there's about 15 minutes on Ebola. Now please just interrupt at any point if things are unclear or you want further clarifications of things, or you want to go off on a particular tangent. That's absolutely fine by me, but just bear in mind we might not get through all of the, depending on how busy you are and this, that and the other. So what we're going to do is we're going to talk a little bit about the malaria work, because this, so it's some of the most recent stuff that we've done. It's some of the work that I'm collectively most proud of myself and our group, and is a sort of culmination of about a decade's worth of development. And it is really, it is the core, if you like, that we will spread out to the big five and the focal three diseases, both in terms of the data and the methods, the covariates and looking at interventions. The results will be in the same type of format. Obviously they wouldn't be exactly the same, otherwise that would not be the best investment of the foundation. And then I'll kind of work on that malaria example to try and fill out what we're going to do here over the next 5 years. And then the Ebola is a nice example of something we were able to do quickly and a different type of mapping. So if we have time for that, if there's not so many questions and diversions in the malaria work, I'll run through that quickly as well. And it'll give you a focus, perhaps a vignette of two very different sides of the mapping that we do. So before we go on to talk about the sort of specifics of malaria and the specifics of Ebola, I want you to think that these techniques could be applied to any spatially variable infectious disease. And why would we want to do that in the first place? This is what I won't read all of this slide, but it helps me structure this thinking for you, is that one of the main things that we like to do, and you can do this in other ways, but we like to do it at the highest spatial resolution you can, is help monitor and evaluate progress once you've tracked the spatial variation of the public health problem of interest. Obviously, if you can take things down to very, very fine spatial resolutions, you're in a much better position to tell people where to go, to target, help optimize the delivery of interventions. And once you've got those, a wide knowledge of that variation, you can do some very sensible things about helping people strategize over wider and wider areas, be those regional, country, administrative, etc., etc. And that's what I mean by helping people act. So the other thing to note is once you've estimated these things at a pixel level, and I'll show you that for malaria in our next example, of course you can then aggregate up to any level of spatial resolution you want with the uncertainty around it. So if you have that as your target in the first place, it's a good place to be, because you can provide advice at all ranges of scales above it, whereas you can't go the other way. One of the things that we hope to do, and we started on the path for malaria, is to help resolve debates about national levels of estimation of the quantity of particular diseases, especially with malaria, and we hope to do that with this other grant that I'll talk about as well. And we'll look specifically not just at the methods and the data and the results for malaria, but also some of the politics around that, and how with maps and evidence you can kind of reduce the degrees of freedom, if you like, about which people argue over certain numbers. If my communication skills fail me this morning, all of what I talk about in this sort of first section of about malaria is in this particular paper. And I do need to call out these people here. Look, there's a lot of people on that list. These are the 3 first co-authors, and this is the lead of this work. So what happens as you progress in your career is you start something off, so we started the Malaria Atlas Project, and then much brighter, younger and able people come and do all the work, and then you get to stand up and talk about it. So that's
the older you get, the farther your name gets along. You're not that old.
So I just want to, from the outset, acknowledge that lots and lots of people did this, and that the real brain trust here, solving some of the big problems, are the first 3, and this one, with everybody else having important roles, obviously. And also to point out that this Malaria Atlas Project is now, having gone from a decade ago to being not a welcome introduction to the infectious disease community, now a WHO collaborating centre in geospatial disease modelling, and since 2012 has provided all the cartographic support for the World Malaria Reports, and continues to do so. So we're starting to go, basically what we do from the outset comes in to become the normative numbers, if you like, rather than sort of academics imposing something from outside. And that's a model that I would like, or will strive to achieve, whether we'll do that or not, for the range of diseases that we're going to talk about in the Big 5. This is the only equation I'm going to show you, and it's not very complicated, and I'm going to talk about it in a quite abstract level. If anybody's really interested in these sorts of things, really happy to go and have beers and dissect all of the bits and bobs, but I'm going to stay quite high level here so that we can cover a lot of territory. And this is essentially how the experimental process is done for the malaria, and I'll unpack each of these in a second. So we have let me start with this. We have this quantity first. So this is the thing that we measure in malaria. So it's PF, Plasmodium falciparum, PR, parasite rate, 2 to 10 subscript here in the 2 to 10-year-old age group. So this is, if we were doing a PF-PR 2 to 10 in this room, I'll take blood from all of you. Obviously, I'd get my consents first. Then I would test you to see if you had a patent parasitemia. That might be with microscopy, it might be with PCR, it might be with any available diagnostic. And then we'd have a numerator and a denominator. I'd also take all of your ages, and then I would standardize and age correct that for the 2 to 10-year-old age group. So we would get a prevalence. It would be, well, in this room I suspect highly it would be 0. It would be 0 over 30 or whatever it might be. And that's the unit of information that we use in this mapping. That defines a baseline, so this is our unit of information here. And if you think about our statistical objective, what we're trying to do is go from lots and lots of little samples in space and time, and we want to fill up this cube of information. So we want to, this will come clearer in the next slides, we want to estimate essentially what the prevalence would be in a room down the corridor where we haven't done any sampling at all. So how can we do that? Well, we can say, from our information, we can say, well, they're fairly close to us. It's more likely that the room next door is going to have a quantity similar to ours than a room over in the mountains over there. And that's where this spatial temporal process comes in. And in all of our mapping, that's essentially what builds us a lot of the skill. So it's Tobler's first law of geography. Things that are closer to each other are more likely to be related, and that gets formalized here. Then we might say there are other things, covariates that we know that help us predict that in that other location. So that room may have many of the similar temperature and humidity profiles to this room, but it's very, very different over there. And if we have information on that, we can also use that to provide skill. We might also say that somebody sprayed in that room and they didn't in this room. So if we have information on the interventions, that can help us be predictive of what might have happened in the other room. And then we have country effects, because we're not dealing with rooms, we're dealing with a continent, so countries have different policies to others, and there's always a residual random variation that we can't explain. The thing just to realise, and why I put it in red here so it reminds me, is if there are no change in our interventions here, our baseline is the same, should be the same as the data that goes into the model. And that will become important in the very last slide about the malaria. If you don't understand much of what I just said there, don't worry, because we are going to unpick that graphically now in a whole series of slides. So here we go again. This is our objective. So we've got all of those surveys that people have done, and I'll show you exactly where those surveys are in a moment, in space and time, from the year 2000 to the year 2015. And what we want to do is make a complete surface for the entire African continent at 5 by 5 kilometers of that quantity. And what we start with is lots of these little points in time and space. So these represent the years again here. And we've got to estimate in all of these little white gaps in between. So we do that, as I've just shown you, with a space-time geostatistical model. And that was a very simplified version of that. And I also indicated that there's obviously an immunity phenomenon in malaria, so us as predominantly adults in this room would have a different expectation of prevalence in children, so we have to have an age standardization model that gets built in a Bayesian way in the data that come in. I also mentioned that there were, and this is where I know when I've forgotten something, when a box comes up here from the first bit. I did mention there are different diagnostics, so we have to standardize across those, and there are various ways of doing that. And they get built into this model, and the uncertainty that's involved in those standardizations gets propagated all the way through. And that's, again, is important in the end when we start to evaluate maps. I also mentioned that there are a whole range of environmental covariates that are particularly relevant for malaria. So we've done a whole lot of work to first assemble those. So we have full space-time cubes. So this is from 2000 all the way to 2015, records of temperature, vegetation, elevation. That doesn't change very much clearly, but all of the kind of standard environmental rasters that you would think that might provide skill in predicting in these gaps. They come from satellites. There's a whole lot of work done to replace estimates with clouds. We do a whole lot of work to take things measured by satellites and turn them into things that are slightly more relevant for biological processes. And then we also do a lot of pre-work to define, both from the literature and through various types of analysis, which are the appropriate set of covariates to use in each. I won't talk a great deal about any of that, although I can do in other domains. And maybe just to make you aware that all of this information, in fact all of the things that we do under the Malaria Atlas project, are open access, and you can have all of that information should it be helpful for anything that you do. And this whole set of covariates I see as quite useful for a whole range of things. So we wouldn't necessarily want anybody to reinvent the wheel there. We then, of course, if we're trying to make this cube, need to know about interventions as well, because we don't, as an international community, we don't just all stand there and let malaria do its thing. We do try and intervene against it. So we also need geospatial models of the current interventions and to be able to incorporate those. And I'll talk about how we do that very briefly. So we need to make full space-time cubes of the interventions as well. Now remember, in that summarized equation, we had the interventions bit, we had the baseline bit, we had the covariate bit, and the random effects bit. And to incorporate that, we also use information from control trials to know, and I will talk about this, how much a particular intervention should affect PFPR, and we can model the impact of that. PFPR is a measure of endemicity of malaria. As a biologist, I'm primarily as a biologist, that's an epidemiologist, that's a unit of information I can get my head around very, very clearly, and it's a unit of information that everybody measures. As a policymaker or someone at WHO or in country, the thing that they're usually worried about is incidence. That's the number of cases. So we have to be able to convert our prevalence value to an incidence one, and I'll talk about how we do that. Sorry, the last bit is, and this is the really important bit, and I think the bit that the group of 4 that I mentioned at the start really did bring into this whole process. Oh, sorry, I don't know what that is. Okay, we're back. And I'll show you what's really clever about this is because once we know what these intervention effects are, we can actually predict what the world would have been like without these interventions, and then we can actually attribute the effect of these interventions to this change, and that was the real important bit of that paper, and we'll summarize that in the final slide. So we're essentially in this talk now just going to run through each part of that diagram, and we'll come back to it again. So this is our fuel. This is our PFPR surveys. You can see that they range from 0 to 100%. They're just a prevalence value. So if they're 100%, you've gone into a community and everybody that you've tested, whether they look ill or not, has a patent parasitemia. And in many cases, which are the true whites here, you'll go in and they're 0. So that gives you some idea of the spatial distribution if you just plonk all of those on a map, although if I asked you without knowing that number to estimate how many points are on there, I don't think you would have got to 27,000. So in this one here, we try and give you an idea from African countries alphabetically here, time in year at the bottom, and you don't need to read any of those. It's the size, it goes from above 250 to less than 1 point, but gives you an idea of how many surveys were available per country. So some countries very, very rich, some countries very, very poor. But what I try and get through to people with this graphic and these combined is that there are a fair bit of information there to make this estimate, and I think it usually is a bit more than people expect. So that's that bit, and that's one of the things when we started the Malaria Atlas project that was really hard to do, was get people to give you their hard-won parasite rate data. So there are about 6 million kids in total, about 7 million people in total. People often sample just children, like in DHS surveys, which is another reason that we chose the 2 to 10 age group, because it makes you have to transform the least amount of data. But that whole part of the process was 2 to 3 years of kind of talking to people, buying people beers at conferences, just trying to be very, very nice, doing the Shawshank approach, which I call is after the film, which is, I don't know if you remember the prison library story. He just kept sending letters and just every week, like a metronome, just keep sending. That's what you need to do if you want people to share data with you. It's easier for them just to provide you the data than to keep getting these damn emails from you. So that's the way that we did it. And then sort of DHS started doing big national surveys, and that was kind of transformative. And most of our data comes post 2000 now in big, lovely, random stratified, stratified by urban, rural in a particular country, and they are the kind of fuel for what we do now and for a lot of the work that we'll extend to. Intervention, not so rich. So this is surveys that have done equivalent thing on BedNet coverage. I don't have time to fully unpack this. This will be coming out in eLife before Christmas, I think. And this is the same kind of graph, just showing you that we do have lots and lots of national information on BedNets over time. But the reason that there's not much back here is that there actually wasn't many BedNets, and I'll show you that in a minute. But we can, and this is the first set of maps I'll show you. And I'm sorry I can't unpack that bit, or it just takes too much time. But we do make full maps of the coverages as well. So this is percentage of people under net in the previous night from 0 to 100. All of this from those survey types that I've just shown you. And this also helps with this counterfactual thing. Year 2000, it basically was no nets distributed in Africa. There might have been 1 or 2 people using those, but as an intervention policy, it just wasn't a thing at the turn of the millennium. And as you go, and you'll see a whole series of these maps as I go through, and the bottom right just shows you the year, and there'll be 15 of them in a sequence. And we just spin through those, and you can see over time what a massive success we've had in BedNet distribution. And I'll go through that again. So essentially going from nothing to, it depends how to describe this as whether you're a cup half full or cup half empty person, but that I view that as quite good progress, i.e. we've changed it from basically nothing to an appreciable coverage of nets, but with some real stark problems in many places. And one of the things I don't have time to unpack is that countries can go up and get a good coverage, and then it soon decays. So BedNets people still have in their mind, I think for reasons that I don't understand, these are like an intervention you give one off and then you go away and problem fixed. Whereas I think they're more akin to vaccines. You need to keep doing it if you want those coverage levels to be maintained. Sorry. So you're going to have to take it on faith about how those bits are done, because I don't have, but we will unpack that geostatistical model a bit more with the malaria work. So we have this, we have all of our environmental covariates in space and time, we have all of our intervention coverage in space and time, and we have all of these which we still need to predict a continuous distribution here. So what we need to do is know how those interventions affect parasite rates, and we have lots and lots of people who've done great trials of those. So we can put all of those together in infectious disease models, and this is a set of those. So we use an ensemble approach, and I'll look at that a little bit more with our prevalence to incidence conversion. But we can say, basically, given a particular coverage of bed nets, we have a function that tells us how much an impact that should have on parasite rate, and we can feed that into the equation, and it uses that to help make the predictions moving forward. So this is this intervention effects model. So this is after doing all of that, and you run it all through on a supercomputer, and it takes about 3 days to run this part of it. We get this. So this is our outcome. So this is year 2000. This is PFPR 2 to 10. Remember the thing that we're trying to predict. This is a continuous endemicity across Africa, and we go from, well, let me run through it, and then I'll run through it and come back. So the way to, when you have these sort of changing maps, to work out what's going on, because there's a lot of information, is to usually just focus on one country. So have a look at DRC. This is my favourite example. So when I started, which was, I'm not going to tell you how many years before that, but quite a few years before that, the prevailing wisdom was that we just couldn't do anything about malaria in this part of the continent because of being Anopheles gambiae, because of where health systems were, etc., etc. So just focus on DRC and look what we've done. For most of that it's true, but look at where we are now. absolutely transformed picture of endemicity, and I'll put the numbers to that. So if you add all of these pixels up in an intelligent way across the continent, endemicity is halved from an average or median value of 33% across the whole continent over those 15 years to 16%. And I'll tell you what that does in terms of incidence in a moment.
Sorry, just to clarify, are these are model predictions or these are actual survey data?
These are the model predictions. So this is, if you do it on the survey data, it actually comes out as a better impact. And there's various reasons for that. I just think there's a bias in where surveys are done. I.e. people tend to do surveys where they expect to find malaria.
Did I notice correctly that the survey data is pretty sparse in the DRC?
It is, but we have good data towards the end because they did a big national survey in 2013.
There seems to be some quite distinct country effects. Is that just the country random effect?
Yep. And that's a really interesting thing. People like nice continuous maps that don't have borders. And I know mosquitoes don't have borders, but countries definitely do, and they have very different national policies, and they have very different bednet prevalences that do change at borders. So I'm quite comfortable with them, with one country being next to another having very different values, and I think that that's appropriate given if you look at all the metrics in a particular country, under 5 mortality can be very different in one side of a border or another. I mean, here would be a classic example around here, some staggering differences between these countries in the south. So yeah, that is exactly that country random effect coming in. Some of the detailed nuances of that are sort of trying to unpick the stories of particular countries we haven't done yet, but it will be a fascinating thing to do. So what does that fantastic change in endemicity mean in terms of cases over that time? Well, this is where you get to some politics, because turning prevalence to incidence is a fascinating subject for lots and lots of infectious disease modelers. And if you choose one particular way, whenever you do publish your map on this, every infectious disease modeler that you didn't choose bashes your maps. So here is our Ewan Cameron and Pete Geffing's what I think is inspired solution to this problem is that, well, we use everybody's model and we take an ensemble from it. And this is just a schematic to say that we used open malaria, IDM's EMOD DTK, and the Imperial College model to convert prevalence to incidence, and that obviously that these change by particular age groups. And if you reverse engineer all of those and test them all on the same data set, of course you can work out what your ensemble prediction is, and then incorporate the uncertainty from all of those in that, and have a genuinely ensembled move from prevalence to incidence. And you put all of those people on the paper, the first paper that I showed you, and then nobody argues about it. So the thing that you do compromise there is you have a bigger uncertainty. But I think actually that's scientifically principled as well, because there is genuine uncertainty between modelled expectations of how they should change, and that's a good reflection of what people think in the literature. There are potentially more models that you could have put on the end here, but we had some sort of inclusion criteria for those, which again you can unpack in this particular paper. So we have an ensembled modelling approach to take that unit of information that's measured broadly across Africa, and to turn that into incidence, and we can do that again through this entire series. Just to point something out in these graphs, note that for most of it, this would be, I think, the classic expectation of incidence versus prevalence of these conditions, so that you have there's this long, and if we put this out to 100%, notice it's curtailed at the 50%, you have this long prevalence, which is the long plateau, which is immunity. So it doesn't matter that your endemicity goes up even further, because essentially everybody's got the disease and they're developing some sort of immunity to it. So you don't really see a big, or this is sort of historically manifested as well, you don't really see a big impact on incidence until if you bring endemicity down from 50 to 40, for example, you'd have very little effect on incidence at all. So your prior expectation on this map shouldn't change as much as the endemicity map. And as you go forward, that is manifest, but it does change in quite a lot of places, because we're down in that business part of the prevalence to incidence conversion. And one of the points that people don't get from this work, but I think is fantastically important, is that we've now, not only have we impacted on incidence, and again I'll show you these numbers here, so huge declines in incidence over that time. So the incidence rate has dropped from 42%, and this is on the model data again, rather than, it has to be in this case, from 402 to 237 cases per 1,000 per annum. And that has translates into a case burden that's about 231 million now, and would have been 265 million in the year 2000, again modelled estimates. And even though that incidence rate has has declined by that large percent, population has also changed in the background as well. So your absolute number of cases has only gone down a little. But we can show you how many cases have been averted, and that will be in the next slide. The big point that people don't or don't sufficiently get from the paper or when I do these talks is this is an absolutely transformed landscape in terms of endemicity. Loads and loads of places on that continent now are at this kind of break point where you can, if you do a little bit more, you can have a really big impact on incidence. And incidence is the thing that takes people to hospital, and incidence is the thing that ultimately leads people to death. So we can, in some of these, what people would have considered completely intransigent malaria places now, are poised to have, I think, an even greater impact in the next decade or so. And certainly a very transformed space from when I started in the malaria world, and just in terms of what was possible in these sorts of geographies. So because we know the effect of, and I haven't talked about this, we have similar maps of ACTs and IRS coverage, so we look at all the interventions. Because we have both the PFPR data and we have a fitted relationship, we can abstract that relationship from the data and generate a counterfactual PFPR. So what would the continent have looked like if we hadn't had any interventions in that time? And this is what I show you in these two maps. And this is the real clever thing, both mathematically and schematically, that Pete and colleagues worked out in this particular paper, and it's something that we'll try and emulate for many of our diseases. So this is the map I've already shown you, the real prediction. And this is what, if we didn't have the Global Fund and we hadn't done any, sorry? Oh, sorry. Artemis is in combination therapy, so drug use, and IRS is in indoor residual spraying, so when people go in and spray houses. And those are the three main interventions against malaria. So we can, and we'll just go through these again. You can see the years in the bottom of each one. And you can see through time the difference between the impact that has had and is real, as defined by the best fit to our PFPR data, and that which we hypothesise would have happened if none of those interventions effects had been known. And then you can see that there's increasingly different look of the continent, which this is our best fit to the data now, versus what would have been if we hadn't. And the reason that we do that is we can then do something really, really nice, which is to look at how much those interventions have done for us, which is what people like the WHO, like people like the Global Fund, and people that, as taxpayers that provide their money that go into these, want to know. Is it, we've invested billions and put out about 1 billion bed nets out there. What's that done for us? What bang for the buck have we got? So this line is the black line is our counterfactual line, so what we predict would have happened without doing anything by way of control. And the reason that goes down is because there's a secular trend in the data anyway. Everybody has a favourite hypothesis to what this is. Some people think it's bits of climate thing going on. I think it's because people have generally got wealthier in that time as well in many of the countries that I'm working in, and there's just a general trend, not a massive trend, I'll admit, but it does go down. The red line is what we've observed, our prediction, our best prediction of the observed change. So we can start to quantify and attribute the effects between BedNets, ATTs and IRS over that period, and then add them up. And if you do that, you get 800 million cases of malaria averted, and 70% of that effect by ITNs. Again, a message not to take home from this is ITNs are 70% more effective than those other interventions, because this is a mix of how much of those interventions were in a particular place, plus the effect that they have. So we distributed many more ITNs than we invested in ACTs or IRS. So it doesn't say ITNs are better, just says over that period of time, given the distribution of resources that we put between those interventions, this is the effect you can attribute to those particular ones. And I think this is a massive public health success story, and I worry that BedNets aren't kind of sexy, they're not a magic bullet, and they're quite hard to do, but logistically hard, engineering-wise, and they're expensive, and all of these kinds of things. But they clearly have had an impact, and I do worry if people sort of take the gas off of this, what we might go back to. But anyway, that's a different story. So we finished with malaria there.
Can you say a little bit about impact on mortality?
No, but watch this space. That is exactly what we're working on at the moment. So I'm doing under 5 mortality maps for the foundation as we speak, and we're trying to then essentially pass that out from this analysis. So that's the number one next research agenda.
Do you wonder whether declining prevalence and incidence might increase the ratio of mortality to incidence?
Yeah, and that would be really hard to unpick from those sorts of data. The reason that one of the sort of natural things, and this is going to be hard to translate in some of the other diseases that we're looking at now, but one of the things that we were able to do this with malaria, of course, is because there were essentially nothing was done in the year 2000. So you've got this, you can model the world without those interventions. In the other ones, there's kind of, and it's an analogous problem, something was done, so you don't have a really clean counterfactual, so we're going to have to make some assumptions in that process. So yeah, very important thing to resolve. So do you want to ask any more questions about malaria before I go on to other things? Yeah. Sorry, there was one in the back first.
I have one question. So if you're looking at age range 2 to 10, this probably is something wrong. Have you looked at the Geospatial ICT? I think that's really going to affect the incidence of infant malaria and really what we're doing symptoms. But because it's one of those interventions that is looking a lot of questions over.
Yeah, all of those things, those interventions that we haven't modelled, and I guess there are a universe of those, will have had an impact in there. And I guess that at the moment they would have been picked up, or they're just given as the sort of the noise. They'll be in the residual. But yeah, it would be great to start incorporating a wider range of those. I think in terms of, you look at the scale of what people have done with BedNets versus some of those other ones, it is likely to be a smaller part of the equation, but I'm not pretending that we've been completely comprehensive in all of the interventions.
Thank you. You've spoken very nicely about what has happened and explaining what has happened. Have you ever been tempted, or have you used this tool to say what might happen next under various policy scenarios?
Yeah. So you move into two quite interesting areas which are extremely non-trivial. Forecasting, in big inverted commas, is I think is an incredibly important thing to do, and something that IHME is very, very interested in a wider context, not just malaria, for the foundation in terms of portfolio management and how we can have some expectations of how the disease burden is going to change between now and about 50 years' time, so that people can plan a little bit more appropriately on which particular, because some kind of portfolio investments, for example, vaccines, have a long lead time. So is it sensible to invest in a vaccine now where you're kind of predicting the disease in 40 years' time to be almost gone? That's the kind of logic behind it. It's, of course, extremely non-trivial to do forecasts in many ways, because the further you get from your observation, I mean, I'm just telling you what you already know, but the uncertainties compound. People have done lots of this work with malaria, and I'm not a great fan of it, essentially because I don't think the baseline models are done rigorously, and for reasons that I can't understand, people don't incorporate interventions in those analyses. So many of the sort of classics, so I'm going to talk about very briefly the climate change thing, and I have to, every time I say this, I have to say, I believe in climate change. You know, the IPCC are a great body, and you know, I believe all of that's coming, and I'm a fully subscribed member of we need to do something about it. I don't believe lots of the work that's been done projecting what's going to happen to some of our infectious diseases as a result of climate change. And the reason is that none of them, and I still think this is true of malaria, none of them, in relation to malaria, incorporate interventions. And as you've seen from that last 15 years, if you don't incorporate interventions, you basically just predict a very different world today. And so my argument to many of these people is, well, why do you choose malaria? Because we're actually, malaria is something that we're doing an awful lot about, and it's just going the other way. Over this century, it's collapsed its distribution by about half, and within that distribution, its endemicity has gone down by half. And that's because of interventions and what we do. So it's not the great rallying child for this particular thing. Now, dengue is the one that I would look at. Everything that we do in terms of climate, urbanization, all of these things are going to make dengue spread and get worse, and that's the one I would focus on. So that particular aspect of the forecasting, I think, has not been done well by the scientific community. And I also think, in an analogous way to where we were with disease burden estimation before some of the global burden of disease work was done, if you do all of these things in isolation, you end up getting fantastic numbers of deaths, and if you sort of add them all up, and there's just not enough people to die from all of these future causes. So I think there is a good argument to constrain those predictions in an envelope, which is a sort of all-cause GBD, and that is going on at the moment, but it's very tentative and very early days. And some of the things are incredible, you just don't have an answer to, like, what's the population going to be in 2040? I mean, we have good projections of those at the national level, but one of the things we're struggling with at the moment is how can we make those projections at pixel level, because that's what's going to be needed to support some of these problems. And if you look and you think, oh, that must be out there, it's not. Nobody's done it. So you're forced to make some quite crude assumptions about those, you know, how population is distributed in that time moving forward, and that of course is going to have all kinds of knock-on effects that you can't control in those predictions. So I think it's important, but I think there are some a lot more principled science that needs to be done in an area, but it's a really exciting part. So I've probably talked much too much about forecasting there.
I just wanted to ask you about how your models are able to account for questions of data quality in the surveys.
Yep. So we tend to, that's really, what we tend to do is get rid of stuff at the start where we don't like it, or and that sounds terrible, but it's, for example, if we get a whole data set back and, you know, there's more numerators than there are denominators, or there's sort of things that we look, just classic sort of error range checks, and we just go, that doesn't make sense. Or there are, they've said it was a sort of, the age range doesn't tally, or it's done at a time of year. That there are many surveys that just don't make so there's an inclusion criteria that I didn't go into. Then pretty much after that we accept things like DHS surveys, so we don't do a lot of manipulation of the data at that stage. So once it's in, it's kind of in, and we don't make as many controls and checks for biases as one might imagine, because we've got a data sparse issue. I think if we unpack those data and look at them per country as to just the raw trends in the data, they're plausible. They're not. It's not that you have a survey done in 1 year and it's one's up here or one's down there. After we do our diagnostic corrections, which is the biggest thing to make sense of the data, and then our age standardizations, they tend to make a plausible story. Well, that's a right story, I don't know, but there's a level of trust that we have to have in the information set, because we haven't gone out and done those surveys. We're sort of hunter-gatherers, if you like. We're opportunistic in what information's out there. I mean, I would love to have the resources to do a fully stratified random survey of the globe, every country. Probably by month would be ideal, and then we'd have the sort of perfect solution. But I guess if we'd done that, I'd also get myself out of a job, because we wouldn't need the maps anyway. So there's a circularity in when we get to a point where we're so rich in data that these mapping become unnecessary. That also becomes important at the really low endemicities, and one of the questions I usually get that you haven't asked yet is why there are discontinuities in the maps at the edges. And we basically have a cut-off at the moment, which we say if it's less than 1 case per 10,000 reported, it's so low that our techniques aren't really well predisposed to work there, and people don't do prevalence surveys anyway. So we cut that off. So as you move into real low endemicity zones, there's a lot of work that we need to do to capture the incidence information that countries record and combine those nicely with the prevalence information. Analytically, that's something we're working on very hard at the moment, and will become more important in some of these other diseases, and will also require a closer attention to those sort of biases between national surveys and reporting. Shall I move on? Big five focal 3. So this has just been funded, and I'm very happy about that. So it was called, it just started out, so you'll all be much more familiar with the foundation than I am, but it started off with these pneumonia, diarrhea, malaria, HIV and TB, and then got called the Big Five, not by me, but by the foundation. And then they asked us to add a group of eradicable, neglected tropical diseases, and didn't define which they were at first. So this is where the title is. And then someone in the foundation called the grant the Big Five Little 3, because it became 3 NTDs, and obviously that wasn't liked by the people that have those particular diseases. So now it's the Big Five Focal 3, which refers to those NTDs. So the vast majority of the analysis is to essentially go global, as we've done for malaria, keep that going and keep that updated year by year. So those full spatial temporal maps with interventions, and then expand that to HIV and TB, but also to pneumonia and diarrhea. Now, I am aware that they are not just one disease, but they are recorded as one disease in many of these national surveys, so we can do a good job, I think, at predicting the envelope, and then how we then distribute those to all the infectious disease causes, or the primary ones among those, is an open area to solve in the analytics. That could be geospatially from lots and lots of surveys where people have done full unpacking of the etiologies of these conditions at particular locations. Or we could use some of the GBD architecture that's done at a national level to start unpacking those things at higher spatial resolutions. But these present a slightly different problem to HIV and TB, but conceptually it's the same process. Collect as much data, relevant data as we possibly can to define endemicity.
It strikes me that for malaria, you don't necessarily have to
I think it would be a help more than anything else, in that you would hope that the spatial rule that we make for malaria will be stronger there, and that we'll have to rely less on the covariates. I think the covariates that we choose for these are quite interesting, so that malaria, and to a good approximation, if you look at many of the studies of pneumonia and diarrhea, it can be forced, that's not the wrong word, are sensitive to rainfall and temperature and these types of things. HIV and TB, you've got a much different epidemiological situation. I imagine it's urban, rural, distance to roads, health systems, all of that kind of stuff. We'll have to build covariates on to get skill in these areas. But it's the same objective, is to 5 by 5 kilometre maps, year 2000 to the year 2020 by the end of the grant, and that those are not just an outcome in themselves, but they're a pathfinder GBD to work out how we downscale some of the GBD work to this 5 by 5 kilometre resolution. So if we can repeat what we did for malaria in what I've just talked about now, globally for those 5, we'll be in a good place with the foundation. Just to remember me to do my acknowledgements there, the focal 3 are human African trypanosomiasis, lymphatic filariasis, and another one that I'm blanking on at the moment, onchocerciasis. So I'm glad I didn't forget. I do my presidential debate mistake.
Yeah, exactly.
Yeah.
The question about the pneumonia and diarrhea. So it seems to me that all the others, there certainly are issues with diagnosis of them, and you don't necessarily know what your true denominator is, but you can always tell, of those who were tested, this many were positive for something.
Yep.
But for diarrhea particularly, and also for pneumonia, the definition of the disease is largely one of a syndromic sort of diagnosis by clinician, which is, as you intervene or as you have policies change, that diagnosis, both numerator and denominator, shift just by virtue of recognition of the syndrome or whatever. There's no way to really know what the numerator is or the denominator. So I just wondered how you're handling that.
Again, I think there's an expectation that we'll pass those out as much as we can, and I think we will. We're able to do that with the envelopes quite well, and I think even just having all-cause pneumonia or all-cause diarrhea in a particular location will be useful enough. So even if we get that as a product, and I just kind of try to manage expectations at the foundation around this, even if we get that, I think that is useful, very useful information. I do think we will be able to make some estimates of that, but they'll have, like you say, some big caveats on them, and they will have confidence intervals around them that should reflect that. And one of the things that I didn't do a good job of here is showing you all the uncertainty maps that go behind some of these. And in some spaces and times, those uncertainties are massive. And we're not shy about those so they're all on various websites and this, that, and the other. One of the disappointments that we have is people don't ever look at those. They see a map. It's not like when people see a graph, they want to see error bars on it and this, that, and the other. When you see a map, you believe a map, and you shouldn't. As you can see with the space-time data, there are some countries and some places where we're very, very sure about what that endemicity is, and there's some places where we're much, much less sure. And that's all in there. So teaching people to how to use those maps is a big part of this process as well. But just one thing to finish on that, even if the map is rubbish in a particular location, and we're not in the business of saying these maps are the be-all and end-all, that is a unit of very important policy information. It says in that country, if you want to do anything sensible about this condition, you need to go and get some data, because there's only so far that we can go for this. And I think that's one of the things that was quite compelling to the foundation, was that this could also be used as an argument to say, well, actually, you haven't had a big national survey in here that's had this component of questions in it for a while. Before we invest in that heavily in this area, we might kind of want some more basic information, et cetera, et cetera. So.
Apropos, since you're not going to get to Ebola,
Yeah.
apropos the quality of data, the DHS survey data could be critiqued as well.
Yep.
Probably pay a lot of attention to that. Again, Leon Mishra, I think, has done a nice sort of overview critique of what can go wrong with these surveys.
Yeah, yeah. Well, one of the classic things in it, which we try and take care of in the analysis here, and again, I didn't have time to talk about, is there's obviously a right time and a wrong time to do a malaria survey in a country, and often there's an expectation to do it at a particular time, but for politics or logistics or whatever, it gets done at. So we need to sort of correct for the time in the year at which a survey was done as well. Yeah, and although there's some expectation that you've got 200 days of parasitemia on average, long tail, but that is not, and the reason that people measure prevalence is it's not so exquisitely related to those, or so temporary, focally related to changes in temperature and rainfall. It is important as to when it's done, and that's just one aspect of DHS surveys that add noise. I'd say that DHS is not the only thing that we do, and we still do all this Shawshank approach, so other national surveys are done. Some research groups have kind of fantastic longitudinal cohorts that we try to get in and all of that kind of stuff. But they are the main fuel for this, so it really is important to be cognizant of those various issues that they have. And that's one of the things I think makes it sensible to move some of these techniques into the wider GBD architecture, because they do a much better job, I think, at the national level of looking at how those DHS surveys compare to the whole range of other information and space-time trends that we have. So I think there is a reasonable expectation that we might use that architecture, at least at the national level, to help us calibrate, if you like, each one of the level of each one of these surveys as they come in. That, of course, assumes that it's an all up or an all down in a particular country, which I suspect it's not. I suspect there are, some teams are great in some places and some in others.
I'm not familiar with the models for translating prevalence to incidence for malaria. Are they dynamical in nature, or do they have a transmission component? Is that a transmission?
Yeah, so they're classic SIR models of the sort of Anderson-May school. They're done in various, EMOD's slightly different, there's some simulation components in those as well, and they all make assumptions based on data of how those all the parts of those differential equations are parameterized. And what we tried to do with this was reverse engineer in that Nature Communications paper. I say we, Ewan, did in that was to essentially reverse engineer everybody's model in each one of these, and to run those on a standard set of data and assumptions of all the parameters, so that our output ensemble didn't have degrees of freedom which was related to being trained on different data sets, et cetera, et cetera. So they're the kind of standard differential equation SIR models that the Swiss TPH, which is the first group, EMOD, which is IDM here, and the Imperial model. And they have literally hundreds of papers describing the evolution of each one of those, and we kind of take the most recent iteration of each of those moving forward. Most of them don't, no. So they're not in this type of analysis, no. Yeah. EMOD's done a lot of work in that area, and I think that's the sort of the frontier, if you like, of much of what they're doing, and of course it becomes increasingly important as we get to low endemicities, of what these last cases are doing and where they seed and those sorts of things. But up until now it's all been well mixed, big populations, all of that kind of stuff. One at the back and then...
Another question sort of related to forecasting, but also a little bit to the counterfactual model. The big five, I think you can see how they're fairly deterministically driven by the covariates. Other diseases like dengue, like Ebola, like other things are probably a little more stochastically driven, where there's a lot of places that would be hospitable to an epidemic, but they don't have them because of random chance that hasn't been seeded by those. Are you able to factor those in?
Well, I think that's probably true for Ebola, and we are able to do some mapping there. I'm not able to talk about that. Maybe we should have that as a separate one entirely. So what we've done, what we would do with a disease like Ebola is to map its zoonotic niche. So we wouldn't say that we would ever be predictive of that stochastic overspill event. But what we can do is say, of the now 25 zoonotic overspills that we've seen in the continent, what range of background range of climates, population, animals, forests make you more or less describe those 24 points, and where are the rest of those in the continent? And that's actually work that we've already done and are developing for the Paul Allen Foundation here. So we can, I wouldn't ever say that we could predict where the next Ebola outbreak is going to occur. That would be crazy. But what I think we can do is say, for the many African countries that have never had an index case, actually you might want to consider that you have the possibility for this, because you have the right bat species, you have the right forest, you have the right kind of rural populations. You've never tested to see if that's in your zoonotic reservoir. So there's a whole branch of mapping, not like these model-based geostatistics, but a whole branch of mapping that we can do to that. Dengue is slightly different again. In the 1950s, it was in about 4 countries in Southeast Asia. I think the first case is in Thailand and the Philippines, the first that we could find, and it's spread globally. So now it's in, I don't think the last count was something like 125 to 130 territories worldwide, and I think it will get to the edges of the Aedes distribution wherever it can be supported, and it's just having this global spread. So there's this, there's one phenomenon there that we can't describe with these techniques, which is there will be other techniques to do so, which is that stochastic spread of those pathogens. But once it's in a country and once it's been there for long enough for it to become endemic, it does again show some quite nice seasonal patterns. There's this serotype thing that also complicates dengue as well. And I do think it is one of those ones where you, particularly if you get urban, rural covariates. So we've done a global map of dengue, and it works quite well, and we've used burden estimates from those. And we tend to constrain that. We don't predict outside where we know it's occurred. But those kinds of maps, I think, would be good indications, and this is some work that we're trying to finish off for the European Union to say 2 things: where dengue might go and might establish as being endemic in the future. So they were interested in that for just Europe, being the European Union. We're going to try and do it globally. But again, sort of criticising some of the work that's gone before, which is what all good academics do and all good builders when they come to your house do, is lots of the predictions about the future of dengue have been done without predicting the future of Aedes. And I don't know how you can defend that. So I just don't take any notice of them at all. So basically you're predicting the future of a disease in a place for which you haven't actually got a vector at this point in time. To me, that seems bizarre. So you have to get if it's a vector-borne disease, you have to do that deterministic part of it first. So that's work that's ongoing on Oxford and will be finished by the end of the year. And then once we've got where we hypothesize the future of the ADs to get, because they haven't finished their global march, we can probably have a more realistic notion of where dengue might occur in the future. I was very upset to hear, as I'm going there for Thanksgiving, it's broken out in Hawaii. I imagine they'll get on top of that fairly quickly.
So maybe we can do, I think there was one more question. Yeah.
Sorry.
Yeah, that's
Yeah.
My question was actually really similar. I'm thinking about someone who might, like, do you actually measure, like, the vector density and where they are? Because someone could get bit in, Western Kenya and then get sick in Nairobi where the vector doesn't live. And so do your models take into account, like, really common migration patterns?
No, it's another big assumption in all of the work that we do, and it's, so this, at 5 by 5K, I think it kind of works, it's okay. If we went down to any finer spatial resolution, that we'd have to start thinking about that really very clearly. So 25 kilometres squared, which is what 5 by 5 kilometres, is actually quite a big area. So you're summarising quite a lot of environmental information. And from what we know about humans' movements, sort of 90% of those in most locations will be within that envelope. We do not take into account the fact that you might have got an exposure from malaria and you go and report it elsewhere, and that is a big Achilles heel in what we do. But it's not recorded in the data that's routinely recorded. So there aren't travel surveys done with all of the DHS surveys. So we can't. Most of it's done in children is another argument I often use. So the sort of 80% of it is in 2 to 10-year-olds. So they tend to travel less than the parents, so not exclusively. So that will be incorporated as noise at the moment, something that we can't describe. And it's something you would really have to think about if you were going to higher spatial resolutions than the 5 by 5K. HIV, important in that as well, so we'll have to think about that.
So maybe before we finish, because I know people were a little bit over, but did you want to comment at all about your plans for building this group and how that's going to look?
Yeah, I mean, I'm kind of always wary about this, saying this in other areas. I know you're recruiting at the moment, but there are as I said, there's one of us at the moment, and the geospatial team needs to build to about 20 or 30 over 2016. So loads of faculty jobs going up, there are loads of researcher jobs going up. Just keep your eye on the IHME website, and if you're interested in geospatial and or you're numerate and have a good a sort of firm idea of the numbers and sort of disease expertise in a particular area, you'd also be a very credible candidate. So, or just write to me informally if you're thinking that you might like a opportunity in this area. Thank you for reminding me about that.
No, and I know a lot of people are. Well, thank you so much. This was really fantastic. And,
Pleasure.
Yeah, I hope we all have more opportunities to hear more and hear about Ebola and then about diarrhea and pneumonia.
Well, now I've seen how lovely your environment is. I need to come here more often. Yeah.
Thank you again very much.
Just very quickly before everybody heads out, this was put on today by the Global Center for the Integrated Health of Women, Adolescents, and Children as part of our Breakfast with WACh series. We have a sign-up sheet over there. If you want to hear more about our upcoming breakfast, you can go ahead and sign up